So here, the timing or sequencing of the input signals is important, as we'll see in the examples to follow. Here, examples of sequential logic circuits are flip-flops, counters, latches, microprocessors. Yes, you can say that pretty much your modern computing is based on something like this, sequential logic. Okay, now this is the part which is sort of the new thing, which is sequential logic. Responds to inputs only when a separate trigger signal transitions from one level to another. So this trigger is called the clock signal. Okay, and I'll come to clocks in a bit, but clock, like, it's basically just another input, just like A and B, but that clock determines how these sequential logic circuits will operate. You can't operate them without the clock. The clock is like the driver. It's like the gate. It's the gate which lets people in or out, or it just lets you change the logic. But unless it's activated, nothing will work. So the clock is very important. So what's the clock? Clock is just zeros and ones, but then you can trigger it based on two things. You can trigger it based on the edges. So let's say that this is the clock, and this is level 0, this is level 1. Okay, here you see that it goes from 0 to 1, so that's a positive edge. Here it goes from 1 to 0, that's a negative edge. So circuits or sequential logic circuits which rely on being triggered on looking at the edge. So there's a clock which is an input besides the clock, and the A and B, which you saw in logic gates, are inputs. Now the A and B will lead to some changes in the output only if it sees that the clock goes from 0 to 1 or 1 to 0. Now, if it is triggered when the clock goes from 0 to 1, it is called a positive edge triggered device. Or it could be also negative edge triggered device. So as you see in some of the timing diagrams, unless it sees that the A and B will not go through, or it will not produce change in output, it relies on the clock to do that. So that's one type of sequential logic gates which rely on the edge. But then there are other sequential logic gates which rely on the just on the level. If it sees it's 1, then it will be triggered. If it's 0, it will be triggered. So these are, let me draw the circuit diagram. This is positive edge. This is negative edge. Then there are again two types. Positive Yes, so CK is the clock. So CK is 1, CK is 0. So these are inputs. Input to sequential logic. Okay, so before we get into flip-flops, when you buy a computer, it says 2.1 gigahertz. Okay, that's basically the clock, which is saying that the clock, that input is going to be fired at 2 gigahertz is 10 raised to 9. So it's 2.1 times 10 raised to 9, it can go zeros and ones. So the faster that clock is, the faster your flip-flops or whatever sequential logic will operate, and the faster your computing is going to be. And so when you shop for clock, you want to shop for, if you care about computations, you want to shop for a larger and larger clock cycle, because that will give you more computations, because the clock is the main driver for sequential logic. Sequential logic goes into your computers and does the computations for you. Okay, so let me just stop here, and we'll get to flip-flop next. But they also have truth table, and the truth table is more complicated because now there are not two inputs, but the third input is Q to CK. Flip-flops. Okay, so a flip-flop is a digital a sequential logic device that can store data Okay, that's the memory aspect of it, and switch between states. We've seen switching as states, zeros, ones in the logic gates too, but storing is a new thing. Switch between states, that is zeros and ones. So let's look at the simplest flip-flop. It's known as the RS flip-flop. Okay, this is the circuit symbol. Okay, so let us look at the inputs. The things on the left are the inputs. So we have an S input, an R input, or rather, let me just put it here. And then the middle one is the clock. Okay, and then on the right side, we have the outputs. One of the outputs is, well, I'll call that Q, and the other one is Q bar. So it's the complement of Q. So then I'm going to copy paste this because a slight modification of this will give me the next RS flip-flop. Okay, so the change is that I just draw a circle. Okay, so what's the circle for? Well, the one on the left is what I would call a positive edge triggered flip-flop, and then the right one is negative edge triggered flip-flop. So clearly that's hollow circle on the right indicates that that's the clock. Okay, here we have the following inputs. S, it's also known as the set pin. R, that's the reset pin. Then we have CK, which is the clock. Okay, and then, well, let me just put it as this. This is positive edge trigger. And then if you have this clock with a hollow circle, it is also the clock, but with a negative edge trigger. Yes, so there are two outputs. Q and Q bar. Okay, now that we have the circuit symbol and we have written down the pins, so 3 inputs, 2 outputs, we can draw a truth table for this. So I'll do that next. Yeah, so in fact, well, there are 2 aspects to flip-flop. Okay, number 1 is there is a truth table like we have for gates. And I'm going to draw that. SR okay, then we have Q bar, and then I'll put some comments which would help us understand this. Okay, so let's go with the inputs, S and R. So S is 0, R is 0. Then I would put here Q0 and Q0 bar. So what does Q0 and Q0 bar mean? Well, when you start the flip-flop, assume that the state it stored was Q0. Then what this is saying is that when S and R are equal to 0, it will remember the output. So the output will be unchanged. Okay, so it does not really do much with the output, but we are sometimes interested in changing the output. So what you need to do is, if you set S equals 1, R equals 0, then what happens is automatically Q becomes 1, irrespective of what was stored in the past. And so this function is known as the set function. You're setting the output to be 1. You could also do 0, 1, in which case it would be, Q would be set to 1, Q bar will be, Q will be 0, Q bar will be 1, and this is the reset function. So think of clearing memories. It's sort of like that, it clears off memory. And then if you go back to 0, 0, it'll remember the state. Now, what if you have 1, 1? Okay, this is not available. You can't use that. What happens physically, I don't know, to the device. It'll probably float, it will not do anything. So R equals S equals 1, not allowed. I believe it just gives you garbage at the output. So this is one of the limitations of SR, which is that you really can't take that input. In fact, that will promote, I'll just put an X in X so that doesn't give an impression that you can put that. You cannot put 1 and 1. So that's one of the limitations of SR, and that's why we will see a different flip-flop called JK flip-flop, which is the one normally used in applications. So this was the first aspect, the truth table. Now, this truth table is by itself, will not work the way it is unless it is triggered by the clock. The clock has this function of actually enabling SNR do its thing. So the outputs Q bar will change when SR are changed only when PK or clock has the correct trigger, right? Which means that if you want, for example, the first one or the second one to be set 1 and 0, and it's a positive edge trigger device, it will only get triggered when the clock goes from 0 to 1. That's for the positive edge trigger. If it's a positive edge trigger device and you go from 1 to 0, then that has no effect whatsoever on the output. So the clock has an important role. Without the clock, you cannot get the JK or any flip-flop to trigger. Okay, so I'll illustrate 1 and 2 with a simple example that's probably will make it more clear. Okay. So here is an illustration. Okay, let's look at a positive edge triggered RS flip-flop, and I'm going to say it is in the state Q equals 0, and which clearly means that Q bar will be 1. So that's the state which you start it off with. And remember that for flip-flop, you need to tell it what state it existed in. Otherwise, there's no way you can figure out what's going to happen next, because it is a device which remembers the values, right? Unless, of course, you reset or set it. Let's say it's at 0 for Q, and then let us look at now what happens. Let's say that these are my inputs, CK, S, R, and I'll use a timing diagram, so it's very easy to understand this. So let's assume that CK goes this way up. Okay, S goes this up, and then R is just 0. 0, 1. Okay, now what we need to do here is figure out how this is going to work. So first of all, we've been told that this device starts with Q equals 0 and Q bar equals 1. So I need to put that. So let's say Q, it starts with Q equals 0. And of course, Q bar will be 1. Okay, so you need to put that because that's how you need to initialize the flip-flops. Now let's try to fill in what happens based on the inputs, which is CK, S, and R. And remember, it's a positive edge triggered device. Okay, so it's triggered when, so it's basically triggered here. So now what will happen is, we know from the truth table, if you go to the truth table, okay, so you see that if it's 0, 0, then it remains unchanged. 1, 0 will set Q to 1. So it basically, if S is 1, R is 0, then it takes on the value of S. If 0, 1, then it takes the value of S. And then 0, 0, it's unchanged. So we just have to look at that in order to figure this out. So let's go back. So 0, 0. Okay, so really we cannot see here. We should see beyond this because we assume that at time t equals 0, this is the state. So 0, 0, we know that, well, because there's no clock, which there's no edge here, this, whatever happens here is not going to really affect anything down at Q and Q bar because there's no edge till this point. So we will see that output will just be what it is. Okay, now what happens is when we come here, S becomes 1, R is 0, and we know that if there's a positive edge trigger for a positive edge trigger device, then a set will go, Q will become 1. Okay, and this will be 0. Keep going. This is set by S equals 1, R equals 0, and CK positive trigger. Okay, now let's just invert this. We have the same case, but I'm going to look at a negative edge triggered flip flop. Let's copy this. So it's the same setup, except that I'm going to change one word here. Or rather, let's keep that. Oh, we can maybe, yeah, we can just change it to negative edge trigger. Okay, so it's negative edge trigger device, same inputs. What happened? What happened is we've seen that here, well, the clock is always 0 or 1, and here we have a positive edge. But this is a negative edge triggered device, which means that the effect of a positive edge has absolutely no effect on the output. And so this will be unchanged. This will remain 0. This will remain 1. And so we expected maybe to change here. No change because this is a negative edge triggered flip flop. Okay, so so this is why it becomes slightly more complicated because now it's no longer about the 2 inputs like we have for logic gates. It's about 3 inputs. And the third input is kind of tricky because you need to see how, in this case, it's the edge which is important, not if it is 1 or 0. So that's something which you need to keep in mind. Now, what I'll do is we'll take this and move on to other examples of flip flops. One of the flip flop is called a latch. And it's a single input, well, 2 inputs, but there's only single non-clock input. So a latch is another flip flop. And I'll show you a way to write everything in one truth table instead of having, earlier I wrote SR and did not put the clock in the truth table, right? I'm going to put the clock here, and there's an easy way of doing that. We'll do that next. So this is a latch, and latch is a level triggered flip-flop. That is, it could be triggered when clock is high or clock is low. It's just triggered by the edge from the clock going from 0 to 1. Okay, so this is triggered. So level means 0 or 1. Okay, so here's the circuit symbol. T, CK, Q bar. Okay, so in the absence of a circle, a hollow circle in front of the clock, that would mean it's a positive level triggered flip-flop. And there's no, the triangle is missing, so it's not an edge. So we have this truth table. D is an input, CK is an input, Q and Q bar. Okay, so since D is an input, we only have two things, right? 0 and 1. Okay, and I said the clock can be, well, 1. By the way, I should put here, this is a positive level triggered, which is important here when we draw the, when interpret this. So we have 0, CK is 1, CK is 1. Now, when we have D equals 0 and clock is 1, remember it's a positive level, so it's triggered by this 1. It turns out the input is going to be, output is going to be 0, and Q bar will be 1. When the clock is 1 for the positive level, and this is 1, we'll have 1, and clearly this will be 0. And then the final one, which is, you could have X, where X means 0 or 1. Okay, we could have clock of 0, or we could have the positive trigger or a negative trigger. Okay, so all these three cases, you will see that the output is unchanged. In other words, it remembers what was sent to it previously. Okay, so you can see that this particular set has no consequence. It doesn't change. The 0 level doesn't change. Now, at the level, it won't change, but after it hits that level, it hits 1, it'll change. So let's look at a timing diagram, just so that we understand this better. Example. Okay, here is D. Okay, so let's see, let's make it. One, two, down, 1, 2, up, 1, 2, down, 1, 2, up. Okay, that's my D. Let's look at CK. So again, this is an input. Let this be like this, goes up, stays up till here, goes down, and then let's just say it remains down. Okay, so these are, by the way, my inputs. Q. Okay, let's say that Q starts. I should put here 1, 0, 1, 0. So it starts at 0. So we are now going to try to see how we can use this truth table in order to figure out what happens to Q. Right, so what we can explain a question is, given DCQ, create the output Q. And for that, we need to look at the truth table. Okay, so here it is. So we look at this. This is we'll assume that this is a positive level trigger. It's only triggered when the clock goes positive. Now here we have 0. The clock is 0, but this is a positive level triggered device. And we know from the third row that this cannot be triggered when the clock is 0, right? It's right here. So it will be unchanged. Okay, we reach here, and then we notice that now the clock goes high. So if the clock goes high, we have one of these two cases. We have D equals 1, which is this, which means that Q will have to go 1. So it's triggered here. It'll go 1. So it reaches here, and then we see that 1 goes to 0. But then the clock is still 1. And 1 means that we should see a corresponding change because we are just still focusing on this part. For clock 1, there is a change. So 1 goes to 0, so will this go to 0. It keeps going. And again, we see that there is a change here. It goes up. Okay. And now what happens is the clock goes down. It's go to 0 level. Okay. But this remains 1. And so what will happen is, because this goes down, that doesn't mean this will go down, because this signal here is just 1. And for 1, output should be 1. So this 1 is correct. It is it basically is the row number 2. Okay, after that, clock goes down, which means that for 0 or negative level, or CK equals 0, there will be no change in the output as shown by row number 3. So this will remain like so. It will not go down, it will remain 1. Okay, so what I want to say is this part is where we see a change. This is triggered by CQ equals 1, and then everything outside that is not triggered, because this is the region where you would expect it to be triggered. So this is row 2, row 1 and row 2. So we used row 1 and row 2, which is right here, to figure this out. Okay, so I went a little bit slow. Let's take it to the next level. Let's do a D flip-flop with a positive edge trigger. And I'm just going to do the truth table. I'm not going to show an example. But then as you see, as we do more and more problems like these, we'll get faster with our truth tables. So here is the D flip-flop. Okay, in fact, the moment I draw this, you should be able to complete the truth table based on what we know of a D latch. D CK Q bar. Okay, so D CK, and we know that this is a positive edge trigger because we don't have the hollow circle in front of the CK. So let's create the truth table from this. Okay, so D can have only 2 values, input 0 and 1. Okay, now this is a positive edge triggered flip-flop, which is it's only going to be activated when the clock goes positive 0 to 1. Okay, so when D is 0, we know that Q is 0. When D is 1, Q is 1. So this is going to be 1, and the complement of 1 is 0. Okay, we know that anything else, 0 or 1 or a negative trigger, no matter what the input is always going to remember the state. So when I say X, it means 0 or 1. Okay, so we could easily write this truth table, and I wrote it because I knew how a latch works. So what I'm saying is, if I give you a negative D flip-flop with a negative edge trigger, you should be able to write it. If I give you a latch with a negative trigger, you should be able to write it because you know something about D flip-flop. Now, here is a way of constructing a flip-flop from logic gates. There are 2 AND gates and 2 NOR gates. And I think this feedback, which you can see here, causes this to act like a sequential logic and not a logic gate, the feedback part of it. So output from Q goes back to the NOR gate. This is a D flip-flop. Okay. Again, the feedback right here causes this to act like a sequential logic circuit. And if you remember, I showed you that these AND gates, if you open them up, you'll see that they have transistors, they have, I think, diodes and resistors. So that is inside these logic gates. But once you have all that thing in a logic gate, you can combine the logic gates and make a sequential logical device. And so you can see the level of complexity in this. So now, if you want to wire this up, you probably don't want to use this logic gates. You'll instead shop for the IC7474, which basically has 2 D flip-flops, as you can see there. Okay, each flip-flop has, we can count, we have T, CK, Q, Q bar, and then you see this PR and CLR. That's actually something which we study for the JK flip-flop. It's basically called preset and clear. It is used to, you just don't want to start a D flip-flop with nothing, right? It needs some initialization. So you can use a preset and clear to set it up. So in reality, you have 4 inputs for a D and 2 outputs. So it takes 6 pins here, 6 legs of the IC. And then this one will take 6 legs. Okay, and then this is not a passive circuit, which is clear from here. This needs to be connected to VCC. This needs to be connected to the ground. You need to see the spec sheet on what VCC you need to connect it to, so what voltage will do. Unless you have that, you cannot get this to work. Now, your computer probably has thousands of these flip-flops, and they're very tiny. Here, the JK flip-flop will be studying next. You can use a 7476. It also has 6, 2, 3, 4, 5, 1, 2, 3. Okay, that's 7. So remember, it has 5 inputs and 2 outputs, Q and Q bar. So it's going to use 7 legs. The right one will use 7 legs, so it will use 14 legs. We have 16 legs. So 2 must be for VCC and probably ground somewhere. Ground. Okay, so now it's really getting interesting because we have now these devices which can go in your computers and you can do things with it. Okay, so let's look at a JK flip-flop, which I think is very important because this is the one which finds practical uses. 4th one, JK flip-flop. Okay, it is similar to RS flip-flop. Okay. However, what the differences are, well, why do we need it? Well, it allows. Let me just put this. It's similar to RS flip-flop, but the reason it's called JK flip-flop is because it has J and K in place of RS. Okay, that's why it's called JK flip-flop. Now, so J is like R and K is like S. Now, one of the big differences that, remember that the RS flip-flop, you cannot have R equals S equals 1. It turns out that for the JK flip-flop, you can have J equals K equals 1. R and S cannot be high simultaneously. But here J and K can be high. They can be high simultaneously. And then the other part, which I think is useful, is that it has a preset and clear pin. To initialize the state. So with the adding those two pins makes it now the truth table is going to be more complex. Right? It's going to have those pins too. So let's draw a circuit symbol, and then we'll draw the truth table. Okay, so J, K, then there's a clock. Okay, I'm assuming that this is I've drawn this for the negative edge triggered, but you could also have a positive edge triggered RS flip flop. Outputs, Q bar, and then I said there's two more preset and clear. Preset, clear. So we have, you can see 1, 2, 3, 4, 5 inputs, 2 outputs. Q bar is J, K, CK, preset, here. Okay, now let's get to the truth table. Okay, so we'll have 5 inputs. Preset, clear, J, K, you put CK, J, K, Q bar. Okay, and I'm going to write it as preset with a complement, just because, if you remember, the preset had like this hollow circle, so it's easier to write it with the bar, so that you can accordingly invert the bar and use it for understanding. So this just makes it more general. If there was no hollow circle, then you can just use the logic here. So preset is 0, 1, 1, 0. Okay, so these particular inputs are used to set the initial state of the JK flip-flop. So here, it doesn't really matter what CK is, it doesn't matter what J is, or any of this, it'll just set it to 1 and 0, 0 and 1. Okay, so this is initialize. Note that it overrides the CK. It doesn't matter what CK is. Okay, next. What about 0 and 0? Turns out that you cannot do this. You should not do this. This is not going to work. It's not permitted. Okay, so let's keep cranking. Now that we have preset and clear is set, now this, if you want this to work like a normal RS flip-flop, you always want to keep preset and clear, the complement of that to be 1 and 1. Okay, so let's say preset clear is 1, 1. The clock goes is a negative edge trigger, and this is a negative edge trigger device, which means that now we are ready to look at different inputs. 0, 0 is going to basically keep the same state, just like the RS flip-flop, where you had 0, 0 for the RNS led to the state being preserved. Okay, 1, 1, negative edge trigger, 0, sorry, 1, let's try 1, 0. That'll be 1, 0. Okay, so that's like the set pin. Remember, set was when R was, S was 1, then you got, sorry, this is like the reset pin. R was 1, then Q will be 1. 1, 1, 0, 1, 0, 1. Okay, now this part is the one which is not permitted in the RS, 1, 1. But 1, 1 is permitted in JK. In fact, what we'll do is it will lead to the complement of Q. Whatever was there in Q initially will be complemented. It become 1 will become 0 and 0 will become 1. Okay, and then finally, we need to understand all the cases where it is not a negative edge, the positive edge, a 0 or 1. In all these cases, doesn't matter what you put for J and K, this will lead to an unchanged state. This is an incorrect figure, right? So this means 0 or 1, unchanged. And this is the useful region. Useful inputs. By useful inputs, I mean that this is how you will operate the flip-flop to do your computations for you. Okay, and then the good news here is that all flip-flops can be constructed using JK flip-flops. Okay, the equivalent for gates is, I think, the NAND gate. If you use the NAND gate, you can construct any gate. Okay, one more thing and we'll stop. I'll show you how to use a JK flip-flop to construct a toggle flip-flop. A toggle flip-flop will just toggle the inputs. It'll make ones, zeros, and zeros and ones. So let's see that, and then we'll stop. Your okay, so what I'm going to do is, this is a JK flip-flop. And let's say that we use negative edge triggered flip-flop. Okay, so far, everything is similar to a JK. Now, what we'll do is the following. Okay, we'll keep the J as 1. We'll keep the K as 1. So the inputs are going to be 1 and 1. Okay. We'll connect this to not gate or inverter. And this is going to be our toggle input. So those are changes. Just draw that in red. Okay, so 3 things we did. We put J equals 1, K equals 1, and put a toggle with an inverter. So what happens is, what does this boil down to? It boils down to this following diagram. So you wouldn't draw it this fashion. Okay, you draw the toggle flip-flop something like this. Q bar, and then the toggle. Now for the toggle, you can see that there is a inverter on a negative edge. So inverter on a negative edge means it's a positive edge. So this will become a positive edge. Toggle is the input. And then the preset here remains as it is. And then you really don't show the J and K. Okay, one more step and we're done. Let's draw the truth table. toggle reset clear Q keyboard. Okay, so remember that the toggle is on the clock. So it is going to be positive edge triggered. So this is the useful input. Preset clear 1. If preset clear is 1, and remember this is a positive edge triggered, which means that we will get something useful to happen, because when you have the trigger as positive for a positive edge trigger, something happens. And so the something here is that it toggles the input. Okay, if you do 0, 1, or negative edge with preset clear as 1, this will lead to no change. Unchanged. This is positive edge, which is also here. Okay, and then we also have to write what happens if you put, let's see, you put 0, 1, 1, 0. And it doesn't really matter what you put here. Okay, remember that preset and clear are used to set the pins to whatever state you want, and this. So does not depend on this. These, because that is used to set the memory. So this is the initialization. Initialize the toggle function. So in other words, the useful function of this is in this mode. Right? If you want to toggle, this is the key line you're trying to use in your whatever circuit logic you have. Okay.